Okay, guys, so we're going to have a test coming up on this stuff. So I'm going to go through your some review things. So your test is going to be, I'll have it posted on probably Friday, maybe even Thursday night, but at the latest, I'd say Friday night. And what the format will be, number one, it'll be open note, open book, and you just do it at home and you'll submit it through Schoology. So I'll post it on Schoology, just complete it on your own, and then, again, use your notes if you want to, and use this test review. And just submit that through the Schoology assignment. If you have any trouble with the Schoology assignment, you can always just take photos of it and send it to me. And if you cannot do it on the page, I know some of you maybe don't have a printer at home to print the test and then do it on the page. Just do it on some notebook paper and send it to me any way you can, and that'll be fine too. So if I don't see your assignment in the Schoology upload, which you should be able to do, even taking a picture of it or something, but if I don't see it in the Schoology upload, then just send it to me on my email, and that'll be fine too. So, okay, so here's what will be on it. Number one, there'll be a problem like this, and we've done some steps of this, but we haven't put it together into one major problem yet. But there will be a friction problem where we have friction, and we're going to calculate the acceleration at the end. Okay, so I'll have one problem just like this one. I'll probably change the numbers in it. And then let me just show you, the next thing will be this multiple choice. Okay, so we've got this multiple choice part that I will also go through all these with you. Most of these questions will show up on the test. There may be a couple that of questions I put on that aren't on here, but not many. And then a couple of them, just make sure you read carefully, because I may tweak an answer, say, okay, which one's the biggest, and it may say which one's the smallest instead. Okay, so make sure you pay attention to those things. I'm not trying to do it on purpose, but the test and this review, I don't have just, everything's not just completely copied and paste. In addition to that, then, there'll be one question where I ask you about to do a action-reaction force, and I will show you that problem here at the end. And then the last thing is you will want to check out in Schoology. Let me find it. Oh, I gotta go through ClassLink for me. There it is. In the week 3, quarter 2 folder down here, you'll go to force diagrams, F equals mg. And remember, we have these force diagrams that I want you to know. Okay, so I'll talk about some of these here in a minute, but actually I'll talk about these here and some of these in a minute. Okay, and then that will be it. So make sure you review those and know how to do these 6 things as well. Okay, so let's go back. And I'm going to get started on this friction acceleration problem first. This should be pretty easy for you. But I know you haven't done it before. So Notability doesn't like my Greek symbols. So this here is coefficient of static friction. Is supposed to be mu s. That is equal to 0.25. And then this one's supposed to be mu k. And remember, S is for static when it's not moving. And kinetic is like kinetic energy when it is moving. Okay, so we got this 20 kilogram box being pushed across the floor, and we've got a coefficient of static friction of 0.25 and a coefficient of kinetic friction of 0.20. So remember, when it starts moving, the friction force gets less, and that's why it's easier to keep something moving when you're pushing it than it is to get it to start moving. So the first thing I want is a force diagram that shows all the forces. So I'm just going to put my box there on the ground. And I've got a force of gravity here. And a normal force here. And I'm going to be pulling it, it says. So it's being pushed across the floor. So we know there's a push in this direction. I'm just going to label it FP. And backwards is going to be the force of friction. Okay, so there's our force diagram for that. Question 2, how much force must be applied to the crate to make it start moving? Okay, so we're using our friction force, and we want the normal force times the mu static. Okay, so I'm going to look up here. Mu static is 0.25. Now, this says it wants the normal force. How much is the normal force? Well, we know that if it's not rising or if it's not falling, then my normal force has to equal the gravity force. Okay, so these two forces have to be equal, and they cancel each other, and that's why it doesn't rise, and that's why it doesn't sink. Now, how much is the gravity force? Well, this thing is 20 kilograms, but that's not force, remember. Okay, so we would have to do Fg equals mg, and that would be our 20 kilograms times 10 meters per second squared. And again, you'll be able to use these notes, this video, or if you want to make a screenshot of it, okay, you can use this for your test. So you'll be able to follow along right along with this. And that means Fg, remember, is equal to 200 newtons. We just multiply by 10, and that also is going to equal my normal force then. Okay? So when I do my friction then using this equation, I'm going to write Ff equals Fn mu static, and that would give me the 200 newtons times 0.25, and that's going to give me a friction force equal to 50 newtons. Done. Next question. It says if a force of 70 newtons is applied to the crate, will it move? Well, the friction is 50. The maximum friction is 50, and I'm going to push with 70. So the answer is yes. And here's a hint. Yours will be yes tomorrow, too. Not tomorrow, but when you do your test this weekend. By the way, I didn't say it. I'll post it on Friday. The test won't be due till Tuesday at midnight. Okay, so you'll have Tuesday at midnight to turn in the test. Calculate the amount of friction, kinetic friction, while it is sliding. Okay, so now I'm going to calculate the sliding friction. And again, it's friction force equals normal force times mu. But this time we want the mu kinetic. So remember, when we start pushing something, it's harder to get it to start moving because my friction will be bigger. And once it gets moving, the friction drops and it becomes less. So my friction force while it's sliding is again 200 newtons times mu k, which is 0.2 now. And I get a friction force that's only 40 newtons. So the friction is 50 that I have to overcome to make it start moving, but then I only have to push with 40 to keep it going. Okay, now it wants me to make another force diagram of that situation. So here we go. And now it wants me to, with their values, okay? So show all the forces on the crate with their values. So I'm going to draw Fg, and now I'm going to fill in the amount is 200 newtons. I'm going to draw Fn. I'm going to fill in the amount, 200 newtons. I'm going to put my push in here. Fp equals 70 newtons. And then I'm going to draw my friction in here. And it is moving, so I'm going to label my friction with the kinetic friction of only 40 newtons. Okay, so not the 50, let me fix that, but the 40. 7, it looked like a 2. There we go, 70 newtons. All right, wants to know the net force on the crate. The up-down forces cancel each other. And again, I don't care if you put this as negative 200 or positive 200, it doesn't matter. Okay, but I've got 200 down, 200 up, those cancel. I have 70 to the right, but only 40 to the left, so my net force is 30 newtons, and it's to the right. And then wants to know the acceleration of the box. So remember, we just do F equals ma. My net force is 30. My mass is not 200, 20. 20 kilograms times A. And I divide by 20, and I get 1.5 meters per second squared should equal A. Okay, so let me know if you have questions on that, and I'll answer anything you have. But that will be the type of problem you're going to do on the test this week. Okay, let's move on then. Pull up the multiple choice stuff. Let's just start at the top. Law of inertia, remember that's Newton's first law. I might ask you that. It says objects in motion stay in motion. Object rest will remain at rest until acted upon by a force. That's true. B will continue moving at the same velocity. Yep. Okay, so Newton's first law says this, that at rest stays at rest and motion stays in motion. It says motion occurs in constant velocities. And it says we'll continue moving in a straight line. Yep. Newton's first law says all of those things, so we are going to circle D. All the above statements are true. Number 2, mass is the amount of force gravity has. No, force of gravity is not mass, that's weight. On a certain matter, so that's false. Remember, matter or mass is the amount of stuff. Or the amount of matter. 3, weight is measured in kilograms. False. Weight is a force, we just said. So weight is measured in newtons. Kilograms measures mass. Weight should be newtons. Number 4, the combination of all forces that act on an object is called the net force. See? Number 5, as an object falls from a very high building. Okay, so when I say very high building, very high building, very high building, okay, this means can't ignore air resistance. Okay, it means we do have air resistance. Okay, so my objects aren't going to hit the ground at the same time necessarily and things like that. Okay, so as an object falls from a very high building, its velocity increases. We know it gets faster. As an object falls from a very high building, its acceleration, remember the acceleration when I first drop it, A equals negative 10 meters per second squared. And as it falls, the acceleration gets less and less until it gets to terminal velocity, where it's not speeding up anymore, and the acceleration is equal to 0. If I change from 10... Sorry, I'm back. Okay, if I change from acceleration of negative 10 to 0, that means the acceleration decreased. Okay, it got smaller. It was speeding up by this much, and now it's not speeding up at all. So we would say that the acceleration decreases. And then next one, as an object falls from a very high building, its normal force. Wait a minute. Normal force is like the thing that holds it up. Remember, if we have something sitting on the floor, and we say gravity is down, normal force is up. So when something's falling, there is no normal force. Okay, for an object to start moving, there must be a net force upon it. Yes, that's just like that friction problem we did before. We had to push with 70, and the friction was 50, and then it started moving. Okay, so that is true. Now, if I said for an object to keep moving, okay, remember, to keep it moving, I only have to match friction. Okay, so the friction here could be, and remember, it changed to 40. So I could have pushed with 40 to keep that box going in that last problem. Okay, tennis ball and a solid steel ball, exactly the same size, are dropped from a tall building. Which ball has the greater force acting on it? So here's my tennis ball, and here's my steel ball. And if I draw the weight of these things, my tennis ball might weigh this much, Fg, and my steel ball is heavier. I'm going to draw that like this. And by same size, they mean they're the same volume. Okay, so they take up the same amount of space. I don't care that tennis ball's a little fuzzy or not. We can put fuzz on the steel ball if we wanted to. Okay, it says, which ball has the greater force acting out? Well, look at the picture. Which one weighs more? Remember, weight is a force. So the steel ball is going to have the greatest force on it. Okay, now, as they fall pretty much the same for the first few seconds, but then the air resistance starts to build up. And the steel ball is going to pull away from the tennis ball and get to the ground first. And it's because I'm going to start getting a little bit of air resistance on both of these things. But they're both still speeding up, and if they speed up, we get a little more air resistance on both of these. And they both keep speeding up. This one's not speeding up by much, but it still speeds up until it gets more air resistance, and so does this one. And now if you look, we're at the point where the air resistance on this one is equal to the gravity. And this thing is at terminal velocity. And it's not speeding up anymore. This one's not. Okay, these two forces have canceled each other, but this one's still only about half the size as the gravity force. So this one's going to keep speeding up and building up more areas, keep getting faster and keep getting faster until this force is finally the same size as that force. So the steel ball will speed up for a longer period of time. So here when it says tennis ball and solid steel ball of the same size drop from a tall building, again, if we did this from the bleachers, the steel ball and the tennis ball would hit the ground at the same time because they'd only fall for about 1 second. It's not enough time for all that air resistance to have an effect. But now it says which one hits the ground last. Now pay attention on your test. I may have asked which one hits the ground first. And I would say last is the tennis ball. Okay, again, that's from the very tall building. At the bleachers, they'll be the same. Okay, and a tennis ball and solid steel ball exactly the same size to drop from, again, a tall building. Which ball will experience a greater amount of air resistance against it? The air resistance you experience will equal the weight. So over here on this one, I only have this much weight, therefore I only got this much air resistance. But on this one I have this much weight, therefore eventually if it falls long enough we'll get this much air resistance. So we're going to answer a steel ball. And that's a little misleading because we know the air resistance affects the tennis ball more. Okay, it affects it more because it's lighter. If I did ping pong ball, that would be even worse. Okay, it would hit terminal velocity really fast because it doesn't weigh very much. Okay, it has a tiny little weight. Okay, bicycle and a car have a head-on collision. The force of impact would be greater on. Don't get fooled. The force on the car is equal to the force on the bicycle. Number 13 says the same thing. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. We know that's true. That's Newton's third law. And most people don't miss this one because you've heard it a number of times. Oh, when one force is applied to an object, the second object applies an equal and opposite force back to the first. Now, I usually ask question 13 first, and everybody puts true. And then I ask the thing about the bicycle and the car, and people answer, oh, the force of impact would be greater on the bicycle. So you read this thing and you say, yep, they're equal and opposite. But then when I ask you about a real life situation with a bike hitting a car, you say, force is bigger on the bicycle. No, it's not. Okay, they're equal. So I always called this the I know Newton's third law question down here. And up here, the but I don't believe it. I'm still going to put bicycle. Okay, so remember, they're the same. Okay, we got skydiver. Now, air resistance, again, we can't ignore air resistance for a skydiver. Okay, a skydiver falls from an airplane. Her velocity increases and her acceleration decreases. Remember, we just talked about that. She starts off with a equals -10, and she eventually gets to a equals 0. Not speeding up anymore. A parachutist falls from a plane. She opens her parachute. She reaches terminal velocity. Then she opens the parachute. Oh, I'm sorry. And before she opens her chute, let's start over. A parachute falls from a plane, and before she opens her parachute, she reaches terminal velocity. Then she opens the parachute. Okay, so here she is. There's her weight. There's her air resistance because she's at terminal velocity, so FF equals FG. And the acceleration is 0. She's not speeding up anymore. Okay, she's going pretty fast. Then the parachute opens. Well, when the parachute opens, what happens to that frictional force here? Okay, well, this thing gets huge. Bigger force. We get a huge air resistance. That parachute catches a lot of air. Okay, so when that happens, now my net force is up. Okay, this gravity might be 200, but the air resistance might be 400. Okay, so the air resistance is winning. Now, if the air resistance is winning, that means it's slowing down, not speeding up anymore. Okay, so it says which direction is her acceleration? Well, the net force is up, therefore the acceleration is up. Those always have to be the same. Acceleration and net force always have to do the same thing. If one increases, the other increases. If one is negative, the other is negative. If one is to the right, the other is to the right. Okay, they always work together. Now, remember, that'll just mean that it's slowing down. Because if let's say my speed is, I'm going to put the negative because it's going down, negative 120 meters per second. And my positive acceleration is a equals plus 20. So what's going to happen? This thing's going at negative 120, but the acceleration is positive. So what happens to negative 120 if I keep plussing 20, plus 20, plus 20? It's going to slow down. So my speed is negative 120, but after 1 second, I add 20, and it becomes 100. And then it becomes negative 80, and then it slows down to negative 60, and then it slows down to negative 40. So every time I plus 20, this speed gets less. Okay, so it's slowing down because the speed is negative, or the speed is down, but the acceleration is positive and up. And then for question 15, it says, in which direction is her motion? That is still down. Okay, when the parachute opens, she doesn't start rising. She's still falling downward, but she's slowing down. Okay, last problem. We've got a graph with velocity. Okay, so velocity in meters per second, and it's showing a few different things. So the speed starts at 0, and then it speeds up to 20. And then it looks like it stays 20 for a little bit right here, not changing speed for a couple seconds. And then it's speeding up again, and then it's constant, and then it's slowing down. The speed goes from 40 down here to 20. And then it stays constant, and then it speeds up a little bit again, okay? So James is pushing a cart across the floor. In which section is he pushing with a force equal to the friction pushing against it? So remember, here's my cart. I'm going to push with some force, and I have some friction going this way, and it says that those two things are equal. So if FP equals FF, what's my net force? 0. And so what's my acceleration? Also, oops, not A. Also 0. Meters per second squared, meters per second squared. Okay, so I want to know where the acceleration is 0. Well, that's where it's not speeding up. So those sections would be here, and here, and here. Now let's see if they're all there. B to C, yes, that's there. D to E, I do not see anything that says D to E here. It would be true, but it's not there. It says circle all that are correct. And then F to G for sure, right here. I'm not sure why they put G to F to get rid of that. It's kind of the same thing, but we can't go G to F. That would mean time is going backwards, so don't worry about that answer. Okay, in which section or sections is the friction greater than is pushed? Now, if the friction is bigger than how hard you're pulling it, it should slow down. So where do you see it slowing down? That's in this section from E to F. That's my slowing down. So we're going to circle that. And that's the only area where it's slowing down on this graph. And if an object is in motion, there has to be a net force acting on it. That is false. Remember, we can have things that are moving at constant velocity. A equals 0, F net equals 0. Or same thing is true with our skydiver in the problem above. Remember, she was falling, and she was at terminal velocity, where FG equals FF. These two forces are equal. That doesn't mean she isn't moving. She's still falling really fast. Okay? But the net force is 0. Okay, so there's that. You can review that later if you want, or use it for your test. And then 2 more things I just want to talk about real fast. So I'm going to go, I think there's some blank page down here. Yep, here we go. Okay, so this is that other handout that we just did, but I'm just going to use the blank space down here. Okay, so first thing, I'm going to ask you about your force diagrams. So first thing is make sure we keep in mind, I think I've done the terminal velocity. There isn't too much with that. Okay, but when I have something flat, gravity is straight down, normal force is straight up. Okay, let's say this is on the table. And those two things equal each other. Okay, now remember, when I tilt this thing, and I've got a ramp, gravity is always still straight down. But the normal force, remember, is a 90-degree angle. Okay, it has to be at a right angle to the ramp. And it's a little less than my friction force. Okay, so make sure you do that. We're going to have some friction I'm sorry, than my gravity force. The normal force is a little smaller than my gravity force. Up here, these two things are equal. Down here, this is not equal to that. Gravity is a little bigger than normal force. And when we get back in the spring, in January, I will talk some more about that because we're going to do some things with angles and sliding then instead of flat surfaces. But remember, we have a little friction here. Okay, and that would be if it's not moving. Okay, so keep that in mind. Make sure if I ask you to do a ramp that you tilt the normal force with it. Okay, so make sure you look over those. Again, those are in, if you go to Schoology, it's in quarter 2, week 3. You will see those diagrams. But most of you have those in your notes if you were in class. Okay, last thing then is I might ask you for action-reaction forces. Okay, so remember, action-reaction forces is A pushes B, therefore B pushes A. Two objects, okay? I want to reiterate that this is not an action-reaction pair. Okay, each one of those has its own reaction force. So here would be the question. I might say, if I call the normal force the action force, name the reaction force. Okay, so we're using this diagram up here. Okay, so I've got my normal force, and I want to name the reaction force to the normal force. Okay, so remember it has to be A pulls B, B pulls A. A pushes B, B pushes A. A hits B, B hits A. Okay, so when I look at the normal force, let's talk about the normal force. What is this normal force? Well, that normal force is the table pushes up on the book. Okay, so it's the table holding the book up. Okay, so that is the one I said is my action force. Now, if I want to do the reaction to that, we have two objects, right? Table and book. Okay, so it's kind of like my table is A and my book is B. Okay, now, if I look at this gravity force, the gravity force is not those same two objects. This gravity force is the earth pulls book. That's not the same two objects. When I say the normal force is the action force, the normal force is table pushes book. So if I want the reaction, all you will have to write is 4 words. Book pushes table down. That is your answer. Okay, so here's the diagram, and I say, if I call the normal force the action force, name the reaction force, you will write book pushes table down. Okay, and that's it. Now, remember, the gravity force also has its own reaction force. So if I gave you the same question, okay, the same table with the same book, and I said that this was the action force, and then I said name the reaction force. Well, FG, this is the earth, object A, pulls book, object B, down. So the reaction is book, object B, pulls table, not table. Book pulls earth up. Okay, so my action reaction have to have the same two objects. Okay, so again, it's like this is object A pulling object B, therefore object B also pulls object A. Okay, so again, just last thing, your test will have one question like this. Okay, it may have another question where I ask you to do a second diagram like this, but I might not ask you to do the action reaction on it. Okay, and then you will have one calculation problem like this, and then you will have the multiple choice questions that are listed on here. Okay, so that'll make up your whole test. I will have it posted probably Friday night at the latest, and then you will do that on your own, and it will be due by Tuesday at midnight. And then I'm available during your office hours. I'm available during your class hours or office hours on Monday if you want some help. Okay, so shoot me an email just to make sure I log in and catch you. But and just give me a time. Okay, so we can do it during your class time, or especially second period if you don't want to get up that early. We can do during the office hours from 2:30 to 3:15 or something. I think I have open office hours. Maybe it's earlier than that, but anyway, I can do about any time on Monday. So if you have anything over the weekend, let me know. Or again, we don't have to meet in a Google Meet. Just shoot me an email question. I can answer it back for you if necessary. And if that doesn't work, we'll get on. But I'm guessing nobody's going to have too many questions. Again, it's going to be pretty much everything I just gave you. Okay, not trying to trick you. Want you to do well on it, of course. So so let's just make sure everybody, again, use your notes, use this video for help, and hopefully that'll go well. Okay, I'll have that posted later.